very briefly, was assessed as having a 3% chance of hitting the Earth in 2029. So far, 2004. It very quickly became clear that it will not hit the Earth in 2029. It will, however, come extraordinarily close to the Earth. So if anybody wants to travel to Brazil, you can see it fly by with their naked eyes overhead in 2029. If you want to make compliments. All right, so I have talked about a lot of stuff, and I think I'll finish up here, and you can also join the questions. Thank you again. Yarkovsky effect. If you had an asteroid that was uniform and on its surface and reflection and perfectly spherical, wouldn't the effect of light from the sun would be to add energy to the asteroid's orbit without necessarily giving it more spin, so that it would actually get into an elliptical orbit over time? So there's a couple of effects. There's direct radiation pressure from the sun, sunlight coming in. That itself has momentum. But there's the Yarkovsky effects of thermal radiation going back out. And I actually meant to also say the asteroid wasn't spinning. So if it was spherical and not spinning and uniform, if it was actually magically completely still and not spinning, then you just have some radiation pressure, and that causes change the eccentricity of the orbit. Right. So that's the Yarkovsky acceleration. But the main effect of Yarkovsky in the short term is to change the in an asteroid that's spinning, some of the light is instantly reflected. And we have to plug this in and radiate heat.
Every year we seem to go through a cloud of meteorites. Why isn't that just sucked into the gravity of the sun? Why does it sit out there?
So it's around the sun, absent some other force changing that orbit. It will stay on that orbit. So we have something like Phaethon, which is occasionally spewing out dust particles that become meteors. They stay on nearly the same orbit. So they tend to spin out a little bit because of things like radiation pressure. And typically the first effect is spin out along the orbit. It's a long string of dust particles sharing the orbit of Phaethon, or whichever other comet or asteroid, and then forms a ring around the orbit. And then the Earth goes through that cloud. They have to spread it around the orbit so that it may be hundreds of thousands, millions, a million kilometers wide. And the Earth goes through the air over the day. We see those flashes for however many hours.
So it is an orbit.
Yes. And unless the eccentricity changes to the point that it falls into the sun or gets too close to the vaporized, it stays in orbit.
Yeah, so late last year there was the cigar-shaped asteroid that got a lot of opinions through NASA, et cetera, on the news, and I was just curious if you could comment on that, what I was referring to, and if anybody else knows.
Is the object Oumuamua?
If anybody...
Okay, so Oumuamua is not actually a near-Earth asteroid.
Okay.
It passes near the Earth, but Oumuamua is something far stranger. It's an interstellar asteroid. So this came into our solar system from the outside. We haven't actually seen that happen before. We've seen asteroids and comets get kicked out of our solar system. Their eccentricity takes them up to the orbit of Jupiter. They fly by Jupiter, they can get just enough energy, they fly out of the solar system and keep on going, like the Voyager spacecraft and the Horizons have done. And they never come back. We expected that should happen around other stars, giant planets, kill the other star systems. You can do this more efficiently maybe. But we've never seen one before. Oumuamua was discovered actually after it made its closest approach to the Earth and was on its way back out. But it became clear it's traveling very, very, very fast. So fast that it could never have been gravitationally bound to the sun in the first place. So that was very new and exciting. SETI actually has a talk about that, which is on the SETI YouTube channel. Several of the experts on the discovery and dynamics of those objects talk about it.
So I was wondering if you can talk about the practicality of maybe using some of the effects you were talking about for either blocking out or perhaps focusing sunlight to deflect potentially dangerous asteroids.
So people are talking, the question is using Yarkovsky effect to move asteroids around?
Yes.
This has been suggested, but it's very, very, very slow. So somebody worked out, I think, if you were to take a container of powdered aluminum, which is very reflective, and you were to coat one side of 1915A, this asteroid I mentioned that has the potential impact in 800 years, you could change the outcome of that, impact, not impact, by 10,000 kilometers over 800 years. That's really slow. And we prefer to do deflection faster than that, if we can. So the gravity factor deflection and the kinetic effect deflection much more rapid. You mentioned what might happen to a person on the surface of an asteroid. I was wondering if you could expand on that, and if there's a kind of relatable analogy or metaphor that would capture that experience, something along the lines of maybe snow. I'm not sure about this because, again, intuitions tend to break down. So NASA has discussed sending humans to near-Earth asteroids, or pieces of asteroids in space to astronauts who are in space. One of the uncertainties was what happens when you grab the surface. I talked about you get electrostatic charge build up. You might end up with some massive dust bunny-like thing where the astronaut touches the surface and now their hands are coated in it, electrostatically stuck dust clumps, and they can't move their belts anymore. That would be really uncomfortable for everyone. But I don't know what a good analogy to that is. Maybe a dust bunny is the best thing I can come up with.
Okay, I'm worried about this asteroid may hit in 800 years. What's the exact date, and particularly how big is it?
I'm sorry?
What is the exact date of that asteroid may hit in 800 years, and how big is it?
I'm recalling that it's March 16th, but I have to look it up.
How big is it?
It's about it's a little over 1 kilometer across.
Okay, and that would do how much damage?
If you go online, you can Google 1950 tsunami. You can see a series of simulations of what happens if you drop it in the middle of the Atlantic. I can't actually tell you where on Earth it will land.
Yeah.
Because we can plot this line where the asteroid can be. We can plot that line onto the Earth, but I don't know how the Earth will be oriented in space at that point because the length of the day is uncertain.
And what's its chance of hitting us?
It's about 1% in the current assessment.
1% less than 1%?
We're not sure if it's somewhere of that order. Maybe we're going to quantify our ignorance here. I think we'll rule out completely that it won't be a problem anymore. All right. We need more data.
I'm open for tax day. So, even at these low densities, why would you not just land a rocket object, a rocket on it with perhaps a just size contact plate, if you will? So, not just push it.
it is a pile of rubble, and you put a rocket engine, press it into the surface, it's not clear how it reacts. So I mentioned the asteroid redirect mission, which was a NASA proposal. The idea there was to pick up a block from the surface of a near-Earth asteroid, something that might probably fit on the stage, and bring that back to Earth. One of the big engineering challenges there was how do you design a system to grab on to a large block that's several tens of tons and move it around space in a controlled way with a rocket. Moving around the entire rubble pile as opposed to a block that's a certain degree of cohesion. That becomes much more difficult. The gravity tractor has the advantage that it just pulls everything uniformly. Is there a question here?
I was wondering if you have to destroy the satellite.
So I talked about how we have to, this is for the impact protection, why it has to be destroyed impact.
Yeah.
So I talked about how we need as much momentum as possible. Momentum is a product of mass and velocity.
Okay.
So if I want to move a asteroid that is 10 million, 100 million times more massive than my spacecraft by a certain amount, I need my spacecraft to be traveling 10 million times, 100 million times faster. So I move the asteroid by a millimeter a second, I need the spacecraft to hit the asteroid at 10 kilometers per second, 6 miles per second. It is very, very hard to make a spacecraft that can survive running into a mountain at 10 kilometers per second.
Yeah, I can understand that. I used to know it's not possible.
People haven't talked about designs for impactors that actually survive the experience, but it's a very hard problem.
Okay.
This is maybe going over the field. As you are mapping all of the paths of these asteroids, has it thought about using them as shielding for missions to land missions to the outer solar system? Because if you could park your spacecraft in the shadow of one of these close approach asteroids for a portion of the mission when you're close to the sun, close enough or close to Earth, you could ride that shadow out to where your shielding issues are less, and you don't have to launch as much mass off Earth. So this is a shield for a manned mission.
And there is a whole separate talk about space resources and near-Earth asteroids, which I didn't have time for tonight. There are several different companies and space agencies working on this, and I talked about how asteroids contain lots of water and carbon compounds. People talk about using those for life-supporting fuel. But one of the other primary products is just pure mass. You take all the rubble piles you don't have any use for, you pile it into sandbags, then you put that on the outside of your spacecraft for radiation shielding for humans who sensitive electronics. So it's been talked about, and there are companies working on it. I just didn't have time to talk about it tonight.
What is the current estimate as to when it is thought that humans could go to Mars?
I am not that sort of engineer. And I want to predict what investments people will make in that particular set of spacecraft. Last two questions, please.
What's the plausibility of mining an asteroid?
So that's the space resources stuff that I talked about. People talk sometimes about mining asteroids for platinum, because I mentioned iridium, which is platinum metal mixed in with the iron, and you got also platinum and palladium and so on. That is actually not valuable enough to be worth mining in space and bringing back to the ground. Instead, the products are stuff to be used in space. So you pull water out of asteroid material, you can use that for fuel, life support for humans. You can pull carbon compounds out, make plastic, make composite material, potentially life support. You can talk about using nickel iron asteroid material for making structural elements. If you want to get really fancy, you can make solar cells out of the silicon, but that's still talk.
Hi, thanks for the talk. And I'm glad you touched upon the space resources side, so we didn't only explore the dark side, if you will, of NEOs. And yeah, we should talk to Andy about organizing another talk on the other side of the coin, the space resources side. But a question, when we did the FDL workshop and we talked about these mitigation strategies, and we had the gravity tug and the kinetic impact, there was a third one, which you didn't touch upon tonight, and I wonder if that is now, for some reason, off the table, or just didn't want to talk about it, it's too controversial, but let's do your nudge, if you will. Can you comment on that?
The project here that Bill was describing was the idea originally developed in the 1990s that you would deflect an asteroid by sending off a nuclear bomb. This is overkill for these smaller asteroids. So you don't actually blow the asteroid to pieces. You don't want to do that because then you have a rubble pile that's going every which way. Instead, you set off a nuclear device a few hundred meters above the surface, and the flash of X-rays and gamma rays vaporizes that whole side of the asteroid, and that gives you a shot on the rest of the mass. Megan Brooks Style, over at Livermore, among many other people, can tell you in detail how that would work. For the smaller asteroids, you've got lots of warning time. It's not necessary. The kinetic impactor and the gravity impactor can do the job without the complexities of such explosives. And also, we're not going to test that ever, because there's international treaties that say we're not going to put nuclear bombs in space. I want to make one final comment, if I may, because I forgot to highlight it during my talk. I want to emphasize just how international and collaborative all of this asteroid stuff is. So you see here all the different space agencies that have been involved in asteroid missions. We have NASA, we have JAXA, the Japanese Space Agency, we have the European Space Agency, we have the Canadian Space Agency, the Chinese Space Agency, and that's not including the many other countries where people who contribute to asteroid survey and characterization are based. Australia, Chile, do lots of stuff in the southern hemisphere, South Africa, and many other places. Because we want to cover as much of the sky as possible and find asteroids in all directions. And then also keep tracking them no matter where they go on the sky. So this is an international and global project by necessity. All right, thank you all again.
evening, everyone. My name is Andrew Facknoy. I'm the Emeritus Professor of Astronomy here at Foothill College in Los Altos Hills, and it's a great pleasure for me to welcome everyone here in the Smithwick Theater and everyone watching us on the web to this program in the 18th year of the Silicon Valley Astronomy Lectures. These lectures, free of charge for everyone here locally, are made possible through the support of 4 organizations that do public outreach in science: the Ames Research Center of NASA, NASA, one of the most redeemed centers in the country, NASA Ames, and the Foothill College Astronomy Program, which offers day and evening classes in astronomy, the Venerable Astronomical Society of the Pacific, an outreach organization in astronomy, and the SETI, Search for Extraterrestrial Intelligence SETI Institute in Mountain View. We're very grateful for their support. Today's program is one I'm especially looking forward to. We're very lucky to have with us Dr. Ashwin Vasavada. He is a planetary scientist at the NASA Jet Propulsion Laboratory in Pasadena, California, and we're very grateful for JPL making him available to our program. His research interests include the climate history of Mars, the weather on Jupiter and Saturn, and boy, is there weather on Jupiter and Saturn, the possibility of ice at the poles of the Moon and on Mercury. Currently, he is the project scientist for NASA's Curiosity rover that began development in 2003 and successfully reached Mars in August 2012, sending back amazing images and data about the red planet. Keep out the
Bye.